Okay, Assalamu alaikum, Shabam. Can you hear me?
Yes.
Yes.
Sound is clear?
Yes.
Yes, clear.
Okay, good. And how about the screen? Can you see the slide?
Yes, we can.
Yes.
Okay, so welcome back to the classroom, ya Shabab. Today, we are going to talk about the first section of the material. I have to tell you that there's going to be a discussion about the the syllabus. Okay, we got some instruction from the university to reduce the grades for some of the elements, whether they are quizzes or so. The university would like to make more emphasis on the distribution rather than clustering the majority of the grade in some element, which is like exam or so. We will discuss this later, I promise. But I thought you should know that we are going to have a revision on the syllabus. Okay, Shabab?
Okay.
Okay. Nothing serious. We might take a little bit from the midterm, put it some time for example, a presentation and so on. That's it. Okay. So let's get started. Today, ya Shabab, as you see in the slide, we are going to talk about what you here see. This is chapter number 3, if you look. And it's about load and stress analysis. This is very important. Actually, the whole course is supposed to teach you how to determine stresses and then how to use these stresses to judge whether certain design is safe or not. That's your ultimate goal, always. So what do we need in order to understand if there is a design which is safe or not? This is a quick outline about the chapter number 3. Chapter number 3 is one of the largest chapter that we are going to have in the course. There are other chapters which are lengthy, but there are ones which are a little bit short. But this one is moderate. So we are going to remind you, okay, about equilibrium, free-body diagram. Then we'll talk about shear forces and bending moment diagram. Hopefully, we are going to do these two today. Then we will, inshallah, next class, maybe today if we have time, we introduce the stresses to you. We'll talk about uniform distributed stresses, normal stresses in beam and bending, shear stresses for beam and bending. We're going to talk about torsion. This part is going to teach you all type of stresses that we might encounter whenever we deal with a machine. Okay. Just wait a second. I have somebody in the waiting room. Okay. Then we'll talk about the Cartesian stress components. And of course, we are going to talk about the Mohr circle, which is also very important element in design. The reason why, this is something we are going to explain. And after that, we are going to talk about the pressure vessel, which by itself, very important topic, as I explained in my introduction. And then we'll talk about press and shrink fit. Press and shrink fit, if you want the truth, these two parts are the most practical parts that you can see in this chapter, because they are real application of industry around us. Okay, I hope this is good enough as an outline. Now, this is a little motivation, which I also touched on during my introductory lecture in the first lecture. But ultimately, why do we want to analyze machine? Listen to me, Shabab. In the end of the day, machines are always complex in shape. Now, running simple hand calculation is going to be a little bit challenging for you. And in the industry, there are always ways, there are codes and standards that teaches design engineers, stress analysts, how to perform a quick calculation. This is practice in the industry. But the real life, this is what you see. You see something which is, this is like an impeller of probably an industrial machine. This is a blower, actually. This is a link of a crankshaft. This is a pressurized cylinder. And this one, what seems to be a part of an airplane fuselage or compartment, something like that. So these shapes are way more complex to be analyzed by hand for us. So ultimately, you will use software. However, we always tell our students that jumping in the software that to produce this nice fancy colors is very critical, very dangerous actually. If you are good in finite element, this is, by the way, we call it finite element analysis, abbreviation FAE. Now, FAE, finite element analysis, is basically a software which enable you to convert geometry like this into little elements. That's why we call them finite. But you have to be careful. They are finite. They are not infinite. Now, if you zoom in, you will see that in this part, for example, there are little elements stacked beside each others. Now, all what you need to do is to know the relation between these these elements and know how to find the stress in one single element. So if you for example look at this element and you can identify the stress, and then you look at this element and you can identify the stress, and then this element, and so on and so on. Now, if you recall from CE 203, you have seen something like this, like an element with sigma x, right? And sigma y, and then tau xy. You have seen this. This is basically what has been done in here, in here, in there. We are dividing this complex geometry into little tiny elements. Each element is almost similar to this, depending whether it is 2D or 3D. This is 2D. If you stack these elements beside each other, each one will have a color, which is red for dangerous, high stress, blue for good stress, something like that. You will be able to analyze the geometry. Now, since we have this software, why do we teach you? Very simple. Because this software are very dangerous. Nobody will pop up from the screen and hunt you when you use this software. The problem with this software, literally, ya shabab, if you put any garbage in them, it will give you a result. So you may get some red, blue, green colors. You think you are a hero, but you may end up doing the wrong decisions. That's why we need to teach you how these softwares were built, how, what kind of equation they use. And we teach you everything so you can, when you use the software, you can judge if what you are doing is correct or what you are doing is not. Do you get my point? So that's very important. Once you master the equation, the fundamentals, the basics, you can go to the software and then you can use them. Okay? Now, so how do we do what we wanted to do? With hand. Little part. If you will see the entire course, we are going to deal with little beams, rectangular bars, cylindrical bars, and that's it. Maybe a hole, maybe a fillet, because these elements are simple enough to be analyzed by hand. But remember always something. We always do the same trick. We solve little problems and then we make them general to understand how big problem can be analyzed. That's the beauty of the science and engineering, okay? So you all know that whenever we want to analyze a problem, it's very important for us to deal with equilibrium. Why? In machine design, mostly, ya akhwan, we are going to deal with summation, equilibrium. Summation of forces equals to 0 and summation of moment equals to 0. These are the two fundamental equations. We all know from dynamics, you have taken dynamics, that the summation of the forces is indeed equals to MA. And for example, if you have Fx, then this is MAX. So why 0? Anybody will tell me?
Maybe we are dealing with static.
Yeah, static.
Okay, well, how about if the acceleration is too high?
But, excuse me, Doctor, but I think the other accelerations in other directions, like in the y direction, will be the same amount. So when we sum it, it will cancel each other.
Okay, that's another answer. Of course, the summation of the moment, if you still remember dynamics, is I alpha. So let me tell you this. First of all, most of the time when we design, like majority of the machines, okay, are operating under an acceleration which is not too high to cause inertial effect. Do you understand? But there are machines which rotate in very high speed. And when they rotate in very high speed, we all know that the centrifugal forces, like turbine, the shaft of a turbine, ya shabab, has blades mounted on it. If there is a crack over here, and this turbine is rotating, which we all know this from the industry, at nearly 30,000 RPM, 30,000 revolution per minute. That's a huge rotational speed. If you convert it into centrifugal forces, it's not little. That little force generated because of the centrifugal acceleration might, propagate the crack until you have the whole thing broken. In that case, you have no choice except taking the inertial effect into the picture. But in here, what are we going to do? We're just going to assume that the design in hand is in equilibrium. The acceleration doesn't cause significant effect. That's it. Okay? Now, if there is, then this is something we have to be treated later differently. Okay? But all of the course, we are going to deal with equilibrium. Just to remind you that whenever we talk about system as a word, we mean an isolated part or portion of a machine or structure. This trick is very, very important. Very important. لأنه يا شباب لما أنت تشوف حاجة معقدة أمامك السيارة, do you think the car when we design it يا شباب like this, do you think we go and plot the entire car together? No, nobody will do that. We will. That's the beauty of a free body diagram. That's the beauty of equilibrium. That's the beauty of system. We can take the crank, ya shabab, the connecting rod for the crank, by itself. We know what are the forces and moment acting on it, and then have it designed by itself. I don't need to have a software engineer, a graphics engineer, and a mechanical to make an entire engine, all the complex motion and friction. No, I don't. All what I need to do is to do that trick and try to estimate what are the forces acting on this guy, then analyze it by itself. So you bring a team of stress analysts, one of them do a little part of the engine, the other one do a little part of the suspension arm, and you do the seal, the roof, you do the hood, you do the wheel, each one part by part. That's why systems are very important. Very important. So why? Yes.
When we analyze a part, so if we're talking about a turbine, for example, are we gonna take the whole turbine in equilibrium and the small parts we can take in motion? How can we analyze?
Well, for example, in the turbine, if you look at the impeller, which I told you about, usually this is, for example, in turbine, we have a shaft. Shaft is the most critical part of a turbine, okay? And we will talk about shaft by themselves in one complete chapter, and we are going to talk about them later. But if you look at the impeller, which is, it's like the part which has the blade and, facilitate the rotation by the steam hitting it and then making it rotate. You will take this part and analyze it by itself. You will take the shaft and analyze it by itself. Now, in here, centrifugal forces will be important. In here, they may not. And we will explain this later. Do you get my point? Okay. So we can't take them part by part. So the isolation, احنا اتفقنا ان احنا we need to isolate the part. So the isolation of one part or a little segment from a system and replacement of the effect of the whole system on that little segment by, forces and moment is basically the free body diagram. That's why the title of this slide is free body diagram, FBD. Now, I have to tell you يا شباب إنه free body diagram is very fundamental. عشان كذا إلى اليوم وإلى آخر إكزام نسويه لو في الفاينل إكزام يمكن واحد من أصعب الأسئلة اللي ممكن نسألها الطلاب هو إن إحنا نقول له ارسم free body diagram. It's very easy, but somehow you take it easy too much, you don't give it enough attention, and you always miss points. So that's why we're going to revise the free body diagram just quickly. Now, if you look at this, this is a very simple machine. The purpose of this machine is to carry the load, which is weight, as indicated over here. Now, we have two linkages. This is link number 3, link number 2. And the meaning of a free body diagram is to isolate each link and then replace the boundary with the proper forces. Period. يعني يا أخوان, let me tell you this. As a mechanical engineers and designers, you should think like this. Let's say this is a wall Okay, and then I have a rod, just a rod, and then on the rod I applied a force for no. Let me hang a weight over here. Okay, now we all know that weight is equal to mass by gravitational acceleration. So if this is 10 kilogram multiplied by 9.81, this is going to be 98.1 Newton. Okay, now if you are a real good mechanical engineer, then I used to call it the mosquito eye. You know, they tell us that mosquito doesn't see us, it only sees the temperature. صح ولا لا? That's why mosquito can feel where are the blood veins, because our blood is warm and they know the place of it. They just see us as this, like spots of red and blue and purple color. So you should have the same eye, but for forces. يعني, if I tell you that this is like this is 98.1 Newton, and this one is 98.1 Newton, you should, without any hesitation, tell me that these two are identical. They are identical. That's it. It's the same. That's the meaning. Why? Because this force will be opposed by a reaction force. It should be equal in magnitude, opposite in direction. That's it. Now, if you want to go to the detail, we know that a fixed end like this will impose a reaction force, F reaction, and a reaction moment. لأنه هذه fixed يا شباب. It does not allow you to rotate. It does not allow you to extend. But because we have a single force over here, then what happened is that we will have only one reaction. So the reaction moment is 0. Otherwise, it's actually there, but its value is 0. Okay, so so if you look in here, this is link number 2. We are substituting it by reaction. We call it RD, and this is a reaction RB. This one is RA, this one is RC. These reactions coming from here, that's it. Now, this point over here in the middle, this point by itself is this. Now, that point, if I enlarge it, it will have been subjected to reaction RB, reaction R, what did we call this? RA, and then the weight is down. So if there is the bolt over here in this point is subjected to all of these forces. But the bolt over here is subjected to RD only. And this one is subjected to RC only. So that's how we draw a free body diagram. Now, why do we need to draw a free body diagram? Well, it's very simple. اسمعوا يا شباب. There are forces. الforces ترى ما هي سحر. There are two types of forces. Those linear ones, which are like F. This is a force, we call it F. And this force, depending on its action, يعني مثلا يا شباب احنا كلنا ندري انه if I have a beam like this and then I put two support and then I apply a force F in the beam, we know that the beam is going to deflect. بالأصح يعني بيصير له bending. صح؟ I can draw the same beam like this, put another pin on the side, bring the same force and put it right here. Same force, same magnitude. But what will happen? The beam will get longer. It will get longer. The same force is causing this tension, this one bending. Also, if you look in the beam, this force is going to create internally what is like a cutting force, which is shear forces. So what happened is this. In summary, ya akhwan, okay, we are in need to understand the forces. What are they going to do inside the body? What's going to happen? Now, look, the sequence is very simple. You have forces, then you put them on a body, then you generate stresses. That's it. Do you get that? Our purpose is to know what are the stresses. We use stresses to measure the strength, the durability, how many cycles this can take, and so on. So we need to know what are the type of forces, and we need to know how to deal with the body. The body is the geometry. And in the sense of geometry, احنا نتعامل معها بطريقة رياضية. فمثلا إما أن احنا نتعامل مع the geometry as A, which is the area, or we deal with it as I, which is the moment of inertia, or as J, which is the polar moment of inertia. That's how we encompass, ya shabab, the body. That's how we do it. The forces are going to be F, which is usually referred to a normal load. V, which is usually referred to a load that's trying to shear off a body. Shearing a body off is like cutting it with a scissor. And then M always tries to bend the body, always. And T, which is the torque, always try to twist it. And that's it. You don't need to remember anything else. Those are the type of forces. So these are the forces. What will happen if we put the forces with the geometry together? We get stresses. Now, what kind of stresses? We all know what kind of stresses. Sigma X, Sigma Y, Sigma Z, Tau XY, Tau YZ, Tau XZ, and so on. Okay. Now, so one of the most fundamental principles that allows us to understand what happens, what kind of stresses are generated in the body, are the shear forces and the bending moments. Now, you may ask a question and say, يعني, why? Why should we talk about? ليش ما نتكلم عن why not? So this will become clear, inshallah, soon. Now, if you look at this quickly, we don't need, because we need to solve some problems today. So if you look at this, we have a beam. The beam is standing right there. Do you see it? I'm trying to highlight it in red. That's the beam, okay? And the beam, for whatever reason, is subjected to F1, F2, F3. Now, the beam is sitting on support. These support will generate reaction. We will call them R1 and R2. Now, because the values the positions of these forces are all over the beam, every single point in the beam will feel something different. Every single point. Now, the question would be this. If you design something, ya akhwan, and you look only at one point, and there are millions of other points, one of these millions of points might have a very critical condition, very critical load. So, how would you be able to calculate the stresses and the strains and the load at every single point in here? How? It's impossible. But we don't need to do that. So what are we going to do? We are going to assume that in a process, we are going to section the beam at every time we have a new force acting. So we look at the beam, let me show you. We look at the beam as a new beam over here, and we say, okay, this is the reaction, all right? Now we can cut the beam over here. We have a reaction. After that, nothing happened. Then we have a force. After the force, we cut the beam. And then we have another force, we cut the beam. And then we have another force, we cut the beam. Each time we cut these beams, the cut, we replace it with reactions. The reactions, conventionally, ya shabab, if you start from left to the right, we assume that V acting downward is positive and moment acting counterclockwise is positive. خلاص يا شباب. Let's make it as a convention ولا نتعب حالنا. نبدأ نقطع من اليسار وعلى طول نعوض V down and M counterclockwise. أبغاكم تنتبهوا لشغلة يا أخوان. إحنا في الديزاين أنتوا تذكروا في CE203 you spend like a month doing all kind of bending moment for beam and shear forces, second order, third order, whatever. We're not going to do this. We're designers. We assume that you know how to do the shear force bending moment diagram. Not only this, even if you are not good at it, we assume that you can use a software that gets you the shear force and bending moment diagram. Your job is just started. You have a lot to do after that. So we're not going to spend the entire term trying to teach you how to do this. Even you will see in the next slide, our method for calculating the shear force and bending moment is very simple. We just want to do it fast because this is just a little step in the design process, okay? Now, obviously, I'm going to remind you that when we do this, we will know what is happening inside the beam at that point. And depending on the behavior, sometimes this value, which is the reaction value, stays constant. Sometimes it changes. So just to remind you that the shear force is related to the bending moment by the equation V equals to the dm over dx. So, and if in the case, if you have a distributed load, which is represented here by Qx, then the change in the shear force is equal to the second derivative of the moment with respect to x, which is equals to Q. I don't want you to remember these equations. We are not going to ask you to even solve these equations. This is just to remind you about these relations. And to tell you that any bending moment that cause concave upward is considered to be positive. Any bending moment that causes concave downward is considered negative. A shear force which causes a rotation, couple of shears that makes the body seems to rotate in a clockwise fashion is considered to be positive. and a counterclockwise is considered to be negative. Do you see that? I'm sorry. I said negative, but I wrote positive. So this is negative. These are just the general rules. Now, if you recall, the relation between the shear force and the applied load is basically represented by this relation. Now, this relation tells you that the change in the shear force from A to B, okay, is equal to the area of the loading diagram between A to B. Similarly, the change in the bending moment is from A to B equals to the area of the shear force diagram between A and B. That's it. That's what I want you to know. If you know this, you're good. I don't want you to remember the equation. I just want you to remember that if you have the load diagram, then the shear force, the change in the shear force is the area under the load diagram, and the change in the moment is the area and under the shear force diagram. So let's have a simple example. Very simple. I'm going to show it to you very quickly because we need to solve a problem together. So here it says, draw the shear force and bending moment diagram for the shaft shown. The shaft is supported by bearings at A and B. Bearings يا شباب. انتوا تعرفون شو البيرنج يا شباب؟ حد يقول لي وش البيرنج في السيارات في المواطير؟
It's what allows the shaft to rotate.
وش يسموه باللهجة العامية؟ السعودية احنا عندنا هنا مسميات كثيرة، ناس تسميه بيرنج وناس ايش تسميه؟ What? I think yeah, Thabit, you're trying to talk or you're Ali, I can't hear you.
يقول سموه
سمير رمان.
يا
سمير رمان.
رمان بلي. سمعت اسماء كثيرة في السعودية. So without further delay, this is what we are going to do. Now look carefully يا أخوان. The beam has reactions over here. The good thing about bearing إنه هو allows rotation. So there is no bending moment or reaction moment. If you apply a force, it will react by that against that force by an opposite direction force. And here you will have RB. Okay? Now, طبعا يا أخوان أنت ممكن تقول طيب how about البندنج هنا؟ البندنج هنا راح يسبب rotation. البيرنج مفروض يمنع الروتيشن فيصير في reaction. This is not how bearing works. Bearings allow for a little bit of rotation. That's why we don't generate moment along this axis, along this plane يا شباب. هذا البلين ما يصير فيه moment. And there is no moment along this plane, of course. Similarly, okay? So, what happened? This is the beam. What you should notice, ya akhwan, is that these dimensions are in inches. So when we write a number 12, we put two ticks. It means this is in inches. So this is the same as a 12th inch. Okay? So this is a 12, this is 18, this is 15. Those are the dimensions from here to there, from here to there, and from here to there. Okay? Now, what happened is this. We have the forces. This is the 400 pounds. This is the 300 pounds. Two applied forces. Look at them. This is the 300. This is the 400. Now, we go back. The bearings are located in these positions. So this is RA and this is RB. We start by equilibrium and we sum up the forces along the y direction, assuming that upward is positive and that this is equals to 0. So we will have RA up plus RB up, which is equal to 700. 700 is 400 pound plus 300 pound. Why it is equals to that؟ لأنه يا أخوان إذا تذكرون يعني إحنا نقول RA plus RB minus 400 minus 300 is equals to 0. So I sum up these and I end up with RA plus RB equals to 700. That's it. Now the next step is to take the moment. This will help me to get rid of one reaction. So what I'm going to do, I'm going to take the moment at point A. Where is point A? This is point A. So if I take the moment about point A and assume that this is equals to 0, then look what will happen. Let me clean up the board. Sorry. So we are going to take the moment right here. All right? So let's look. This one will cause no moment. صح؟ احنا نعرف الفاليو حقت الرياكشن. Yeah, sorry شباب. I should do it up. Sorry. We are trying to determine the reactions. Over here. So this one will cause no moment. Now, RB will be multiplied by that distance, causing a moment in this direction. However, 400 will be multiplied by this distance and it will cause a moment in this direction. 300 will be multiplied by all of this direction and it will cause a moment in this direction. So this one is opposite to them. That's why we have RB. So let me clean it up so you can see it. So RB multiplied by what? By 30. What is 30? Is 18 plus 12. Good. And then which is equal. خلاص يا شباب. هذا باتجاه equal يكون الاتجاه المعاكس. So what do we have? 300 by 45. هذا 300 by كم؟ 12 و18 و15. 45. And then we have 400 multiplied by 12. You have two equations and how many unknowns? Two unknowns, RB and RA. So you get RB and you get RA. This is now the complete diagram, free body diagram, with the reaction determined. صح ولا لا؟ 90 pound و 610 pound acting on the upward direction. Now, when you determine all the reaction, you are now ready to establish the shear force and bending moment diagram. We start with the shear force diagram. To develop the shear force diagram, أول حاجة, this is the shear force, V in pound. This is X in inches. That's number one. Okay? Number two, we start by the reaction, which is 90. So what do? We go from 0 all the way to 90. And then what happened after 90? All of this distance, there is nothing except 90. So I'm going to continue as constant. Then all of a sudden, I have 400. 400 وين يا شباب? Acting downward. So I have minus 400. I have 90 as positive. Minus 400, how much is it? Minus 310. So I go from 90 to minus 310. This length, ya akhwan, from this point to this point is equals to 400 as a magnitude. طيب الآن هنا ما في شيء فشو يصير؟ كل حاجة تمشي constant until I reach this point. This point now In here, I am at minus 310, and all of a sudden, I add what? 610. So, minus 310 plus 610 is going to give me how much? 300. So, I go all the way to 300. Now, this one is a plus 300. Nothing happened until I go to minus 300 and I reach to 0. If you recall in CE, they told you the shear force diagram has to end with 0. If you do not reach to 300, then there is something wrong. Go and repeat it again. خلاص يا إخوان؟
تمام.
Okay. نيجي حق المومنت الآن. المومنت هي الاريا under the shear force diagram. So, let's do it this way. أول حاجة, what is the moment? طبعاً هنا المومنت هي M pound inch, صح? Force by distance. الأكسس هذا هو X, which is in inches. So, the moment at the point over here will be 0. ليه؟ لأنه ما في distance يا أخوان. يعني أنت لما يصير عندك البيم وفي force هنا وتاخذ المومنت هنا, what is it? There is no distance. There is a force, but there is no distance. So the moment will always start at 0 and will always end at 0. You get that يا شباب؟ هذا رقم واحد. طيب أنت الآن تعرف إنه المومنت في الحقيقة هي الاريا under this curve. طبعا الاريا هذه شنو؟ هذه 90 اللي هي قيمة الشير فورس multiplied by this distance. This distance is 12. So 90 multiplied by 12 is the area, right? Which is equal to 1080 pound inch. Understood? طيب وين نحط هذا الرقم؟ إذا كانت هنا 0, this is how we do it. أول حاجة, إذا كانت الاريا هنا constant, يعني you have a straight line, معناها إنه the integration of this constant is a first order equation. First order equation هي عبارة عن y equals to ax plus c. In another word, it's a line which has a slope. So I don't need to know what is happening here. All what I need is what is happening at the tip. The tip is 1080. So if I know that this is 0, and I know that this is 1080, كل اللي يحتاج أسويه إن أوصلهم خط مستقيم. انتبهوا يا أخوان. لو كانت الاريا under the shear is triangle, the area here you might reach the same value, but the line is not correct. A second order here, a first order here will be converted into second order here. So you may have a concave upward or concave downward curve. Do you understand?
Yes.
So what are we going to do? We have 1080 and we draw a line between them. That's it. So we go to the next step. The next step, we have all of this area. هذه الاريا هي عبارة عن minus 310 multiplied by 18. Okay? Now look, how are we going to do this? The moment over here, we call it M2, okay? It is M1 plus minus 310 multiplied by 18. Do you see this? So you have to understand that you will start from this point. You have to add it in. So what happened? You have 1080 minus the multiplication of these two numbers is 5,580. If you subtract them, you will get minus 4,500. This will give you the point right here. It's a minus. Again, because this is a straight line, all what you need to do is to connect this with a straight line. Now, I think you know what to do. In order to find M3, look what we would do. We have to have M2, this one, which is minus 4,500, plus this area. This area is 300 multiplied by 15. So we have minus 4,500 plus 4,500, you get it 0. So you are perfect. That's it, ya shabab. Next class, we are going to solve another example. Yes?
بس عندي سؤال بسيط. Suppose that there is a moment on the point that where the force is 90.
Applied.
Yeah,
Yes.
applied. Okay.
Yeah.
And
we are, just to cut it short, that's what we are going to do next time.
Okay.
We need an applied moment, okay?
Okay.
An applied moment. It will
Yeah.
cause a jump. Don't worry, we are going to solve this next class, inshallah. Okay, shabab?
Okay, inshallah.
That's now 10:50, the end of the class. Thank you so much. We'll see you next class.
شكرا لك يا دكتور.
Have fun.